Swayam Prabha. Digital India. Educated India.
Hello and welcome back. In this video we will look at bagging, continuing from our lecture on decision trees. So, all the figures in this presentation are provided by Intel Software, and the material is inspired from Introduction to Statistical Learning by Gareth James. Based on what we saw last time about decision trees, they have a tendency to overfit the data. That is, it performs very well on training data, but new test data sets arise and the errors are huge. So, basically it is a high variance model, that is another way of looking at it. So, it is high variance. So, one solution to prevent overfitting in decision trees was to prune the trees, but it helps reduce variance to a certain point, but beyond that it does not help really, and the effects are not very significant. Okay. So, bagging is a procedure that is developed to improve or to reduce the high variance of decision trees. So, we will look at how it does. So, the idea behind bagging is to train a lot of decision trees on a given data set. Okay. So, we train a multitude of decision trees and combine their predictions to reduce the variance, right. So, if you have this is based on this very simple concept that let us say you have data points z1 to zn, and your variance on individual data points is sigma squared. So, if there are n data points and if you look at the mean, the variance of that mean is sigma squared over n, right. So, as you increase the number of data points, your variance on the mean comes down. That is the concept that is exploited with bagging. So, you train a lot of trees on a given data set and you take the average of these predictions if you are training regression trees, or you combine the predictions for classification some way or the other. So, where do we get the data set for training these multiple trees, right, because we have only one data set. So, ideally what we would like to do is to have multiple measurements, and with each measurement, when I say measurement, you collect data 100 times, and with every data you collect, you train a decision tree. However, that is typically not possible because you are generally given a data set or only a set of data is available, and you have to grow your tree based on that. So, the way to train multiple trees is to grow decision trees from bootstrapped samples. Okay, so, what do we mean by bootstrapping samples? That is what we are going to look at. So, there is this data set. This is about movies and their budget, the turnover, total gross take, who is the director of the movie, the rating, and so on and so forth. This is a movie data set. So, we are trying to make some decision about this based on this data. So, we will not go into that detail just to understand the data set. So, the way we go about doing bootstrapping is to select a subset of this data with replacement. So, if you look at this particular, so the blue area is the sample data. So, the idea behind bootstrapping is to sample your given data with replacement to create a new data set. So, if you look at this particular movie database detail, so there are 17 data points and we are selecting a subset of this data marked in blue, right, with replacement. So, we do it, let us say capital B number of times. So, B bootstrap samples are generated, and we use each one of these B bootstrap samples to train a decision tree and use the output of the decision trees let us say as an average or a voting scheme to get at the desired result. So, the way it works is, so if you look at this particular realization, we have a different subset marked in blue here. We have another realization of the data, that is a sample of the data which is sampling a different portion of the data here, as well as in this case another sample of the data. So, you can sample different subsets of the data with replacement, and with each subset you can train a decision tree and use the output and average the output for classification, for regression, and some voting scheme for the decision making. So, if you do that, what happens, what is the nature of the data sets that we get when we do this kind of sampling. So, on average, let us say if you have this is in this plot, you see this axis basically the number of bootstrap samples. So, each time you select 10, 20, 40 or 80 or 100 samples from your data, and this is the probability of a particular data set, data point not being present in the data. Okay. So, that is given by this expression here, 1 minus 1 over n raised to n. So, if you look beyond a point, as the number of bootstrap samples increases, so we see that typically every bootstrap sample contains 2/3 of your original data, and 1/3 of your original data is not present in your samples on an average. So, that is the makeup of your sample data. Now, this again this is possible because we are sampling with replacement. So, just to reiterate, as you increase the number of bootstrap samples, you see that the number, the percentage of data left out is like about 1/3. So, 1/3 is not selected. Typically your bootstrap samples are made up of 2/3 of original data. Okay. So, this refers to the individual data points, right. So, we will exploit this fact to do error estimation later on, but we will just see how we can go about doing this using these bootstrap samples for training decision trees and obtaining an output. So, we have, let us say in this illustration, we have about multiple trees, okay, and each of those trees are trained on one of the bootstrap samples, bootstrap data sets, and there is an output corresponding to each of those trees. Let us say this is a classification task. So, each one of these trees outputs, let us say it is a binary classification. So, we are looking at either red or blue, right. So, each one of these trees outputs for a particular data point, it outputs the decision. So, 2 of the trees said red and 1 tree said blue. Okay. So, then you can, so for a classification task you can just do maximum or the voting scheme. So, since red gets the maximum number of votes, you would classify that particular data point as red. Okay. So, similarly we can do this for all the data points. So, for every data point, so each one of these columns is a data point. So, every data point, each of these trees will output a certain category, red or blue, and we assign a category which gets the maximum number of votes. So, as you go along the rows, as you go along the columns, each column you will select the category which got the maximum number of votes. Okay. So, this is for a classification task. So, in the end you will get a single classifier. Okay. There is also for instance regression, wherein you will just get take the mean or the average. Okay. So, there are many ways of going about this. If you think about it, let us say think of a classification task, then based on the output of the individual decision trees, you can formulate these output probabilities, which is nothing but, so let us say there are 3 classes, then you can have the probability of class 1, class 2 and class 3, and each as the fraction of the trees which gave this as output, class 1 as output, right, the fraction of trees that gave class 1 as output. So, so people, there is a, I mean you can do it this way, but the better way would be to actually get the raw probabilities from the output of the tree itself, right. So, for instance, each tree will output a certain class with the probability that you can calculate, okay, based on the leaf which is to which it is assigned, and you can actually take the average probability over the leaves of every one of those trees and use that as to classify into a particular class, okay. But this is even though this is appealing to do, the better approach would be to directly estimate the probability from the output of each of the individual trees and then average those probabilities instead. In this case, we are considering the fraction of trees that give a particular class as output, okay. So, in the end, so what are we doing? We are bootstrapping our data set, and with each bootstrap sample we are building decision trees and aggregating the output of those decision trees. So, it is bootstrap. So, bagging is nothing but bootstrap aggregating, okay. So, that is the idea behind bagging, and the what it improves is the high variance. So, it brings down the variance in your model because decision trees tend to overfit. So, having a multitude of decision trees trained on the similar data will give you a better average output. So, one of the ways of calculating the error or validating your machine learning algorithm, as we have seen earlier, is the cross validation that we k-fold cross validation or n-fold cross validation. It is kind of difficult to do, as you can imagine, with the bagging approach. So, what would be the typical approach taken in for when you are using bagging, right. So, we saw that about 1/3 of the data samples are left out on an average when you, in every bootstrapped version of your data set. So, once you have created a tree based on the subset of the data, you can measure the error on the unused samples. So, okay. So, let us say you have about 100 trees, right. Okay. So, let us say 30 trees do not use data point, some data point, I will call it x 40 or something. So, let us say you have 120 data points. So, x 40 is one data point, x subscript 40 is one data point, and 30 of those trees do not use that. So, then you will evaluate the error on x 40 on those 30 trees individually and average them, okay. So, that will give you, so you can, for every subset of trees that do not use a particular data point, you can use those trees to evaluate the result for that data point and use that average as a measure of the error in your algorithm, right. So, this can be root mean square error if you are doing a regression task, or the classification error in case of a k-fold or a two-fold classification, okay. This procedure is called the out of bag error estimation, correct. So, that is one of the, this is one of the advantages of using bagging. So, you do not have to specifically do k-fold cross validation, you just have to identify data points that are not used in subset of the decision trees that were used for the bagging procedure, and you evaluate the error using only those trees on that particular data point. So, you can like that you can identify almost 1/3 of your data set on an average as not being used in one tree or the other. So, then you can use you can accumulate the error over all those data points and calculate an average, okay. That gives you either for classification or for regression. Similarly, you can do same procedure for feature importance, right. So, feature importance can be either measured using the classification error, or typically the Gini index will give you the measure of feature importance. What do I mean by that is, we saw that we are looking, when we are trying to do the split at every node in a tree, we are choosing features based on the largest change in the Gini index or the entropy or the classification error. So, if we can identify, so it is the same procedure as before, but we on the unused data set, but we will use, instead of accumulating the error, we will accumulate Gini index change and average that over all the trees. Okay. So, that way it will give you a good idea of which feature is the most important. So, recall that it is much easier to do this if you have a single decision tree, because at every node, whenever there is a split, you know the change in the Gini index or the entropy that you have, or whatever criteria that we have used to make the split, and you can use that as a measure of feature importance. Okay. But when you are doing bagging, that is when you are averaging over a multitude of trees, maybe several hundred of them, then it is very difficult to do that in a straightforward way. So, because the data set will keep changing between trees typically. So, then we just have to do a similar procedure that we did for calculating the output of the tree. So, instead of averaging over the root mean square error or the classification error, you look at the Gini index and you average over that for every feature using data points that were not in the training data or in the data that was not used to make that tree. Okay. So, you can do that for. Now, recall that when we were talking about this decision trees, we also looked at something called feature importance. So, we figured out that the feature that was the most pertinent to the task at hand was the one that gave the biggest information gain as measured with the Gini index, for instance. Okay. So, this was our way of figuring out the most significant features in our data, right. So, when it comes to bagging, it is not one decision tree that we are looking at, we are looking at about hundreds of trees, and then it is very difficult to make this decision. How do we figure out which is the most important feature, right. So, here again we do exactly something similar to what we did earlier for calculating the out of bag error. So, we will look at the average information gain, right. So, we look at the average information gain over all the trees for that particular feature, and that gives you an idea of if that feature is very important or not. Okay. So, during the process of training, like we saw, we take bootstrap samples and train every tree with it for every tree, and whenever we make a split on the data based on the information gain, we keep track of the information gain for that particular feature across all the trees whenever that feature is used, and we take an average of that, and that gives you the feature importance when you are using bagging as for classifying, right, or even for regression, right. So, typically bagging performance increases with the number of trees. Okay. So, if you have about 100 or more, it is stated in many textbooks and on resources that about 100 trees should do it. Okay. You should be able to get a good average, in the sense you can reduce the variance significantly if you use about 100 trees to fit your data. Okay. And of course, you can always measure the error using out of bag error, and you can also look at feature importance just by even averaging across the trees. So, the advantages of bagging, they are same as decision trees, they are easy to interpret and implement. Okay. You do not have to do any pre-processing, especially for bagging, right. Whatever pre-processing you do to the data, centering it at 0 unit variance, those things that you do for the data, it remains the same. So, all the data, there is no extra data pre-processing or anything of that sort. And of course, doing bagging improves the variance, and there is less variance in your output, and training multiple trees can be done in parallel because they are all done independently. There is no correlation in the training. So, that way, the training of one tree does not depend on the training of the other. So, you can train multiple trees simultaneously. Of course, you do have to implement them in a certain programming construct. So, that there is no this can be done very quickly, right. So, bagging is a very useful tool to have, especially if you are using with decision trees, and many of the Python packages come with it. So, you can try scikit-learn or any other Python module that offers bagging inbuilt. So, we have looked at decision trees, and we also now looked at bagging, which is basically just exploits the fact that if you average over a large number of trees, then you get a better variance. But the problem still exists, because if you see, we are sampling the data with replacement and the process for growing the trees remains the same. So, if you consider a situation wherein a certain feature, let us say in this case a director, okay, of the movie, in this case in this data set, has a significant impact on whatever classification that you are trying to do with it, and that is the most important feature. So, even though you are selecting bootstrap samples of data, the first split is going to be on the director, right. So, that way all the trees that you train are correlated, and if you average over a bunch of correlated variables, then you are then you do not get such a huge reduction in variance. Okay, so that is not great. So, if your data set is like that wherein a certain feature has a huge impact on the classification output, then it does not really help. So, to alleviate that problem, we will look at what are called random forests. Okay. And random forests are just another variation of, it is not exactly a variation. But random forests, what you do is the same thing, you train a lot of trees, but then you will not only select the data points at random, you will also select the features at random, and that helps to weaken the correlation between the trees that you train and improves your output. Okay. So, we look at this in slightly more detail, and following random forests we will also look at a gradient boosting and ADA boost. And these techniques are also generally very powerful for improving the accuracy of whatever classifier that you might be using. We will look at these in the next few videos. Thank you. Hello and welcome back. So, in this video we will look at random forests, so which is based on banded decision trees. So, we saw that bagging can be used, or bootstrap aggregation can be used to improve the variance when you are using binary decision trees. This is by training a bunch of decision trees using bootstrap samples of your training data. Okay. So, because binary decision trees tend to overfit, having a very large number of those, the variance is reduced, and it performs and improves generalization performance. Okay. However, the problem with bagging is that it is possible for trees to be correlated, in the sense that if we have a very strong couple of strong features which always split first, or most of the most what do you call, the best information gain is obtained by splitting on those features, then no matter how many trees you average over, that they are correlated. So, beyond a point, bagging will not reduce the error in your predictions. Okay. So, this is primarily again to reiterate, because there will be some more few indicative features or a bunch of strong features which lead to maximum information gain, and averaging correlated variables will not help reducing the variance. So, in order to deal with problem, we do something called random forests. As I guess the name implies, it is again a bunch of decision trees, but there is a difference from how we do with compared to bagging. So, with bagging we grow decision trees from multiple bootstrap samples. So, this is here is our training data, and the blue highlighted area is what we are choosing as the training data as part of the entire data set, and the blue region is where we choose the training data from. As we saw the previous lectures, this is just the movie recommendation database. So, the date of the movie, the title of the movie, the budget. So, you have date, title of the movie, budget, the domestic total gross, the director of the movie, the rating and the runtime are given, and so we are just choosing this this subset highlighted in blue as our training data. Okay. So, what we do is we select with bagging, we just selected with replacement random samples from the training data. So, that is basically we bootstrap the training data to produce. So, if we have one set of training data, we produce, let us say in this case 3 sets of training data from the original training data. So, as you see, the blue box keeps moving around inside this white table, which is the actual total number of data sets available to you, and with each bootstrapped training data sample you will fit a tree, a binary tree. And we saw, and we won't go into details, but we saw last video how we for a per given test data set we will run the test data set to all the trees that we have trained using the bootstrap data, and we will just average, or in this case maximum voting for classification and average for regression. Okay. So, for random forests again it is the same principle that we will grow decision trees from multiple bootstrap samples, with the exception that, so even the features will be chosen at random. So, let us say we have, let us say look at this particular tree here, which is trained using this particular data set, a bootstrap data set highlighted in blue. We will not use all the features. So, at the root node I have cut out these 2 features here, these 2 columns of features. Okay. And when we come to the particular node here, again I have cut out some of the features. Let us say this, I left out the title feature again and grown a decision tree. Okay. So, the difference between this bagging and random forest is that from a very top level viewpoint is that when we grow these multiple decision trees from bootstrap samples, not only do we bootstrap the training data set, but we also only choose a subset of the features available to us at every node in your tree, in every tree. Okay. So, what happens? So, this kind of reduces the correlation between the trees that we train. Okay. So, that is the principle behind random forests. So, it is a modification to bagging, wherein we grow decision trees from multiple bootstrap samples. Let us say we have m data points, we will have bootstrap samples m data points, and for every tree at every split we will consider only a random subset of features. So, let us say you have total of n features, we typically use small n, I have used capital N here, that is fine. Let us say d features, and typically d is order of square root of n. Okay. So, at every node in a decision tree, in every decision tree you will only choose a subset of the features. So, the learning on the subset reduces the correlation between the trees. Okay. The disadvantage behind using a tree like a random tree this way, like basically building a random forest from trees which are trained on bootstrap samples as well as randomly chosen features, is that it becomes difficult to interpret. Okay, because every node, even though even if we grow all the trees to a particular depth, every node might be split based on a different variable. So, it will be very difficult for us to interpret which variable gave the best information gain and things of that sort. Okay. However, there is a huge improvement in performance compared to bagging, because we are decorrelating the trees that we are training. Okay. So, we typically would train hundreds of trees, and as we saw in bagging, for a regression output we will consider an average of all the trees, outputs of all the trees, and for a classification output we will do maximum voting. Okay. So, this is a brief note about random forests. Again, the fundamental principle is a decision tree, just that how we train them and how we interpret the results are the only difference. Okay. Thank you.